So this is a Falcon problem of rotation. So we're going to follow the Falcon method to solve this problem. So we have a pulley here. It's got two little radii. So this outer one corresponds to a mass that's hanging off a string, and the string was wrapped around the pulley. There's a mass M1 hanging off of it. And there's a mass 2 hanging off of a smaller radius here in the center. And we're told that this whole pulley has a moment of inertia I, and we can't include that in our answer. This should say N and I here. We can't include that in our answer. So let's follow this method. So you should always trust in the Falcon. So the first thing is F. So F stands for free body diagram. And whenever you're doing a Falcon problem, if there's more than one object involved, you have to do a free body diagram for each object that you care about. So in this case, there's three objects. There's M1, there's M2, and there's the pulley. So for M1, we always want to ask, are there any long-range forces? So M1 is experiencing a gravitational force, Fg1, and there's a tension force that's touching it, and that pulls up. And let's call this T1 and T2. So there's a tension force pulling up. And there's nothing else touching that mass, so those are the only two forces. M2 is similar. There's a gravitational force, Fg2, and there's a tension force, T2, pulling up. And these tensions aren't the same because this is not a massless pulley. So we have to treat them as though they have different tensions, and we could figure out what they are if we wanted to later. So finally, the pulley. So if we were to draw a free body diagram for the pulley, there would be a force exerted at the center of mass, mg, for the pulley, and there would be a little force from whatever, like, pin or whatever is holding this pulley up that points up. But when we do the F equals ma and torque equals ma for the pulley, we're going to use torque, and we're going to put our pivot at the center. So for my pulley, those two forces in the middle are there. So there's an mg, and there's basically a contact force from the little pin in the middle. But we're going to not end up worrying too much about those forces. So on the left, the ones that we care about, there's the T1 that pulls down. And then at a radius R2, there's another tension force that pulls down over here. And that should be all the forces that will matter in this problem. So A stands for two things. A stands for acceleration and axes. So when you have more than one free body diagram, you can define a different coordinate axis, a set of coordinate axes for each of those three situations. So in this case, I'm going to choose mine to be a certain way so that my acceleration constraints are easier. So basically, if the pulley rotates this way, I want to call that a positive angular acceleration for the pulley. And if it rotates this way, I want to say, okay, the acceleration A1 is positive. So I'm going to put my positive y-axis down for this M1. If this is a positive acceleration, angular acceleration, this mass will move up, so it's A2 will be up, and so I want that to be positive also, so I'm going to put my positive y up for M2. So if I were to indicate the axes in these three cases, this one has positive y down, this one has positive y up, and the pulley has positive alpha is counterclockwise. So now that means that if my angular acceleration is alpha, I need to relate that alpha to A1 and A2. So if I have an alpha of some magnitude, how will I figure out what my A1 is? So if I go through a certain number of radians here, this will translate some amount down. And those two things are related by alpha is going to be the linear acceleration of this m1 divided by r1. And in the same way, alpha will be equal to a2 over r2. So a1 and a2 aren't equal, and you can kind of see that by, if this pulley is spinning, if this mass moves a certain distance, this mass won't move as far because it's taken up less string than has been let out for m1. So those two accelerations are different, and indeed they are. So we're going to end up wanting to replace a1 and a2 with alpha, so I'm just going to solve this for a1. a1 in terms of alpha is r1 alpha, and a2 is r2 alpha. So I'm going to use those two relationships later. So those are my constraints on the acceleration. If you defined your axes to be a different way, you would just have to make sure that you get the right negative signs in these equations so that if this is positive, this has the right sign. All right, so the next thing is the laws. And the only laws that we have here are that Fg1 is equal to m1g, and Fg2 equals m2g. And now we're ready for our components. So nothing for m1 and m2, nothing is happening in the x direction, so I don't need to worry about that. And the rotation of the pulley is either counterclockwise or clockwise, which is basically one-dimensional, so there's no issue with components there either. So it's now time to use the net force acting on m1 is equal to m1a1. We'll do the net force acting on mass 2 is equal to m2a2. And finally, we'll do the net torque acting on the pulley is equal to I of the pulley times alpha. So for m1, we come back up here and we look at our free body diagram and the way that our y-axis is pointing. So it's pointing down, so the force is going to be Fg1 minus T1 equals m1a1. And we can substitute in a couple of things now. So Fg1 we said was m1g1, and a1 is equal to r1 alpha. Whoops. R1 alpha. So that's one of our equations. Here for the second mass, this one will have T2 minus Fg2 equals m2 a2. So we have T2 minus, now we can use this, m2g equals m2a2. And finally, our torque equation. So there are two forces here that are going to exert a torque around the center point, which we're going to define as our pivots in the middle. So T1 is going to exert a torque that's positive, it's counterclockwise, and the torque from T2 2 will be negative because that's going to tend to rotate it clockwise. So that's the I of the pulley times alpha. And torque is R cross F. So the R goes from the center to the point where the force is applied. So that's R1. And these are at a 90-degree angle, so the cross product just gives us R1 times T1. So this is R1 T1. This one is going to give us R2 because it's acting right here. T2 equals I times alpha. That's our third equation. So now we have three unknowns. Our unknowns are T1, T2, and oops, I did forget to substitute A2 with R2 alpha. So, okay, so now I do have three unknowns. I have T1, T2, and alpha, and I have three equations, 1, 2, 3. And now I just have to do algebra until I can eliminate T1 and T2 in order to solve for alpha. So to do that, I would solve this for T1, I would solve this for T2, and I would plug both of them in here and here, and then solve for alpha. And alpha will show up on this side. So you have to gather all the alphas on one side to solve the whole thing.